Okay, this is the replacement video for the segment in the live session where the slides are missing. Sorry about that again. And packet loss. Where does it occur and how we measure it? So it occurs right here at the end of the queue. The situation is this. At the router, the output link often operates on a limited capacity. And the incoming traffic could be higher than the capacity. In that situation, packet will have to queue up. Over time, the buffer space will be exhausted. When the queue is full and there are more packets like the blue one over here comes in, the router will drop the blue packet. And that's where we see packet loss. Now, some systems might retransmit to recover from the loss. For example, having the router right before the loss occurs to retransmit the packet, or go all the way back to the beginning of the connection, the source end system, to retransmit the lost packet. Now, some other systems might just not bother, as a best effort service. Second, to measure packet loss. And by the way, we neglected to talk about how we measure packet loss as well in the live session. So good to have the replacement video. So the way we do the measurement of packet loss is very similar to what traceroute does. We send probes to a node. Ask the node to send a reply back. So count the number of probes sent, count the number of replies coming back. Divide replies to probes. We get the packet reception rate. Once subtracting the packet reception rate, we get the packet loss rate. So that's packet loss, how you measure it. Next, throughput. This is the third metric. So it's actually trying to catch a rate of something. Now, transmission rate and throughput rate, they actually use the same units, bits per time unit, bits per second. But transmission rate is actually accounting the number of bits a node can transmit out onto the link. But throughput is actually to account for the bits to travel end to the other end at the receiver. Okay, so throughput is more the receiving end. And there are two ways to measure instantaneous throughput. So that is the receiving rate at the given point in time, very short period of time. Average throughput is essentially an average of multiple instantaneous throughput over a longer period of time. Okay, now let's focus back down to the scenario below here. On the left, this is data center. You see this is a file server and it has a hard disk serving files of this size. On the right is the client asking for files, and this is also the receiver of data. Along the way, there are two links. This one closer to the server operates at RS bits per second. This one closer to the client operates at RC bits per second. Now, let's try to represent the link capacity using thickness of a pipe. So this case illustrates RS has a lower capacity and RC here has a higher capacity. Now, one can also think of, hey, the hard disk here as a water tank. So, user here drawing files down from the server is equivalent of a household drawing water off the water tank, isn't it? So, a thinner pipe here will limit the rate that the household receive the water in the end. And that should make it easier for you to answer this question. What is the average end-to-end throughput for the scenario? RS smaller than RC, so thinner pipe here, thicker pipe here. Water comes in here. The amount of water comes out then will be limited by RS, even though RC is big, but only the receiver C is RS. The other way around, big pipe at the beginning, thin pipe towards the receiver. Lots of water is going to come out here in the middle. But RC here being thinner, again, limits the amount of the water that can come out to the receiver. So you see, thinner pipe, both limiting the amount of waters that can reach the receiver, therefore limiting the end-to-end throughput. There's a special term for these narrow links, the bottleneck links. They are the links on the end-to-end path that constrains the end-to-end throughput. In this even more general scenario, you'll see, let's say, bunch of servers up here, clients down here. Let's say we have 10 of them, okay, running simultaneously. And let's assume that each of the connection is occupying a fair share of the thick pipe in the middle of the network. So for each flow, the end-to-end throughput can be estimated this way. The minimum of each of the segments capacity, RS, R over 10, and RC. All right. Now, as to which quantity tends to be the smaller one, it really depends. If the company providing the service is actually not that rich, then RS could be the bottleneck. If the household trying to download the file is lower in terms of income, chances also higher that RC is the bottleneck. So that was throughput. Delay, loss, throughput. 3 metrics to quantify whether a service is working well on the internet. And we also talk about how we measure or estimate, okay, for the quantities. Next subject is actually not that technical. It's called the protocol layers. What we are trying to achieve there is more to try to organize these pieces we've already talked about, so that it's easier for us to grasp, easier for us to relate different notions. So let's try to organize pieces a little bit. This is kind of important because internet engineers will still need to communicate. So it is also to help us discuss. Now, before we move on to talk about internet, which is complex, let's use an example which we know well and is also complex. How about that? So this example is the air travel network. So the process of doing air travel is this: a series of steps starting from looking up the web, finding a cheap ticket. You purchase the ticket. At the time you need to travel, you go to the airport and then you check in. So the check-in counter might give you a baggage claim ticket in case you're checking a bag. In the meantime, you get a boarding pass. With that, you can enter through the gate on board the plane. On the plane, you might hear the flight attendants announcing that, welcome aboard, this is flight something, 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 and we'll be taking off in a few minutes, things like that. And then the plane will be buzzed off and take off. Most of the time you spend in the air travel is to have the planes routing through the sky. Okay. So you'll be sitting, having your onboard meal, chatting with friends, while the pilots communicating to the regional control. Okay, so airplane routing services mainly executed by the pilots. Eventually, the plane will land. Upon arrival, the pilot might say that, hey, welcome to something something international airport. Please remain seated until the buckle sign is off. Yeah, once that light is off, and some of us wouldn't, just stand up without the light being off, then begin to grab our bags and then walk out of the gate and go straight to the baggage claim. Now, if everything is all right, you exit and that's all. Sometimes you couldn't find your bag. Then you bring the claim ticket to the baggage service and they will look things up for you. So, if we talk about the series of steps sequentially, it would appear that there's no connection. But now I kind of laid them out in this U shape. You might have observed a pattern, a certain structure. That's somewhat implicit. Ticket, ticket, but now more explicit, isn't it? Baggage, baggage, gate, gate, runway, runway. So they are now looking like layers. And each layer implements its service and more or less independent of the other layers. Okay, so it implements its own internal service, somewhat independent, but still having certain connection to the other services. So what we're trying to do here is to try to lay a complex internet in a similar fashion. So there's an explicit structure that allows us to easily identify the relationship between these pieces. Okay, this is called the a layered reference model. Okay, and in the live session videos, you see that I recover this slide. So go back there and continue watching the live sessions video. That's all for this one.